Okay. So at this point, we're actually going to start is we're just going to delete structure B. We don't need to worry about that. We can look up at structure A. What do we have? I'll accept that in this case. We got a pi bond. What does the pi bond act as? A nucleophile, or technically a base. Okay, what is it reacting with? BH3 and THF. What is the role of THF? It's just the solvent, so we can largely ignore it. So we're really looking at BH3. Does BH3 look like an acid? Why not?
I don't think boron is very electronegative.
Right. So a couple approaches we can do to kind of nitpick our way through that one. If we happen to know the electronegativities, okay, boron is actually not very electronegative. In fact, it's less electronegative than hydrogen. So what does that mean about the electrons in those boron-hydrogen bonds? They're going to the hydrogens, which means the hydrogens carry what charge? A partial negative. So if our pi bond was to act as a base, we would need positive hydrogens. Those aren't positive hydrogens, so that doesn't make any sense. So our pi bond's not acting as a base, it must be acting as a nucleophile, which therefore then means our boron structure needs to act as an electrophile, which is also problematic considering that the hydrogens are negative.
But the boron is positive.
Okay. So one option we could look at is that boron is also going to be generating a fairly large partial positive because we have the electronegative oxygens connected to it. Not a bad approach, but a couple things should kind of pop up within that as potential issues. Is hydrogen particularly electronegative? No. So even though boron is lower in electronegativity than hydrogen, you're still looking at the bottom of the bottom, which means the difference in electronegativity is fairly negligible, which means that partial positive is not particularly positive. Yeah, I'll just leave it at that. Okay. So if that's the case, what happens? Well, all that information kind of goes away. Whoops, we bring in some hidden information. So how does this react then?
This is to do with the THF then, right?
No, the THF is just a solvent. And I'm being a bit misleading. I fully accept that. No. Ish, but no.
The boron, the pi bond would donate its electrons to the boron. So
Why?
Because it's...
I mean, does that mean that it should be simultaneous?
We'll come back to that. Why is the boron electrophilic? We just went through and said the hydrogens aren't very electronegative. They're not taking electrons away, which means that's not a very positive boron. And if it's not very positive, it shouldn't be electrophilic. Why are both of you telling me it is? Why do you want to add a lone pair? Push on that a little harder. I'll come back to you, I think.
Does the boron have a charge?
No, it has 3. Yeah.
The boron
Does it-
does
does it-
not have a charge.
Does it take 3
Why
bonds?
why do you want to put a lone pair on it? Common bonding? Well, what's the common bonding pattern you're driving towards? Why do you want to have a lone pair there? Why do you want this?
Because then it would act as...
No. Why does that look better than that? We're going to come back to that.
Because it can act like a nucleophile without any problem.
No. Why do we want to put the lone pair there? What's the number one thing you need to do with Lewis structures? Octets. Every single time you want an octet. Yes, I want an octet, so I want to put a lone pair there. But before we start getting excited and just randomly starting placing lone pairs, how do we draw Lewis structures? Like Didn't we already learn? Yeah, you learned this, so it should be real fast. How do we draw Lewis structures? What's our first step for drawing a Lewis structure?
Electrons?
Count our electrons. So how many valence electrons does boron have? 3. How many valence electrons does hydrogen have? 1, but there's 3 of them, which means the total valence electrons I'm allowed to put into this is 6. 3 plus 3 gets me 6, which means, should the lone pair be there? No. So I don't want the lone pair there. There is no octet. Okay? Or boron's octet, if we will, which is a little bit strange to say, is happy, quote unquote, at 6. Okay? How does that change its chemistry?
I mean, it doesn't have electrons to really donate.
Yeah, it doesn't have electrons to donate. Okay. So it shouldn't act as a nucleophile. No radicals. Even more review. What's the hybridization of the boron?
Oh, fuck.
It's sp2. And if it's sp2, what's left over? A p orbital. And are there any electrons in said p orbital?
No.
No, which means what could you put into said p orbital?
Electrons.
Electrons. And if we put electrons into that boron's p orbital, what is the boron acting as?
Electrons.
An electrophile. There's the chemistry for our boron. Okay? All of OChem 1 shows up again. Okay? And we either choose to learn and process that content so that we can apply it out in a new scenario, or we have to go through and memorize all of the detail. Okay? And I know we keep saying this, but I'm going to keep saying it. There's 2 approaches. You memorize or you apply. We struggled with application. You struggled with memorization. That results in 0 points. That's a problem. Okay? You need to pick either one. I don't really care. And move your... I do care. Actually, I don't want you to memorize it. Okay? But I get it. You can try and memorize your way out. You need to remember that content and you need to push forward with it. Okay? When it comes to class time, I'm going to make you apply. There's no really ways around that. I'm going to say you have to apply. We're going to have to work our way through it. Okay? On your own time, you can memorize. Okay? To help with that memorization, if you don't know what this reagent does, what should you do?
Look it up.
You need to look up the reagent. Where do you find that reagent?
In that weird sheet that you've got.
Weird sheet that I've got. That makes me very confused. I don't know what that is. What weird sheet do I have?
Isn't there a sheet that we can look stuff up in that you have? Or
I think technically this one is in a weird sheet. I don't know where that weird sheet is, to be honest, but maybe you do. So yes, go for it. Okay? And if you don't want to use the weird sheet because you don't know where it is and I can't help you find it, okay, maybe you should talk to Anthony. Okay? Go to your textbook. There's references of all the chemical reactions in the entire textbook. Look for your boron reagent. Okay? You could narrow the field. What is this boron reagent reacting with? It has to be reacting with the alkene. So if you can identify the alkene, you can now narrow the field. You're not looking for carboxylic acid reactions. You're looking for alkene reactions. That can help you sort through. Is that process going to be insanely frustrating? Yeah, that is very frustrating. Okay? The point is to build up a little bit of frustration in you so that you do what? You memorize it and you don't have to do that process ever again. Okay? Having the answer spoon-fed to you does not help you. You have to have some of that kind of counter-emotion associated with it. Okay? If you're going to hold on to it for any reasonable amount of time. Okay? So, we've got our boron acting as an electrophile. We've got our alkene acting as a nucleophile. Those electrons could dump into the boron. Technically, I like green arrows for our mechanism, so it could dump in. Okay, what would happen then?
Wouldn't it kick out a hydrogen? Because now
Okay.
its octet is exceeded.
Why would it kick out a hydrogen? That's a neat idea.
Wouldn't it be simultaneous?
Okay, it could kick out the hydrogen because it's exceeded its octet. Okay, let's work with that so we could add that arrow in. Where do I want to attach the boron? Because there's two carbons of the alkene that have electrons. Technically, I've got the middle one or the end one. You want to go to the,
Least substitute.
why do you want to put it at the least
It's
substituted?
got the least electrons around it. Or, oh, fuck, oh, shit, I mean, wait,
I mean,
it's got, shit.
I'm trying to process what you said.
That's
I think
That's
what
what
you
the
said is
negative-
okay.
I think, I know it's weird, but it makes sense.
Okay. So I believe what you're saying is you're looking at the resonance of this structure, and you think it's better to have the negative charge here and the positive charge here, the negative being more stable with less electrons around it.
Yes.
Awesome. Okay. So cool. That's fantastic. That's great. That works. Okay. Which would mean we would be building a positive charge at the secondary carbon. Okay. As you suggested, the boron has exceeded its octet, and so it would kick off that hydrogen as H minus. Well, what's the problem with that?
It's extremely reactive.
Yeah. H minus is a trash leaving group. Are there worse leaving groups? Not really. That's pretty much it. That's the bottom of the barrel worst leaving group possible. Which suggests what about your suggestion for the mechanism?
It'd be trash.
That'd be trash. Okay, so we have to change it. But
It's a positive that it could attach onto.
if you've said it leaves,
Means it exists on its own.
it exists, period. So you could go through and say, well, now it can go in and do this. You've still established that H minus exists on its own, and that's bad. You can't do that. Okay? But you threw in something else, Anthony. What else did you say?
That it would be simultaneous.
Simultaneous. I don't want the hydrogen leaving on its own, because if it leaves and exists on its own, that's a bad mechanistic step. But what I can do is I can have that hydrogen, or technically hydride, instead of just leaving, I can have it immediately react back. What happens then? Well, there's no carbocation, and I now have my hydrogen connected to my structure. Okay? This actually gives us an interesting piece of information that is relevant for other reactions, not for this one, unfortunately. Okay? Where is the boron relative to the hydrogen? And don't tell me they're on opposite carbons. I get it. That's fair, but that's not what I'm asking. That's still referencing which carbons.
Same plane.
Better. Okay, same plane. Okay, so if I add a little bit of information and I call this boron wedged, what must the hydrogen be?
Wedge.
It must also be wedged. Because of how this reaction is happening, that boron and hydrogen are sitting directly on top of the alkene, which means when I do all the bond breaking and bond forming, they have to be aimed the same direction. Could it also be dashed? Yes. Okay, what's the relationship potentially between those? I said potentially. Enantiomers. Okay. In this particular case, do we care?
No.
Why not?
They're not chiral.
They're not chiral. Okay. So the wedges and dashes are ultimately irrelevant for this particular reaction. We don't have to stress about it. But when we move to, say, an ACS exam, when they ask about BH3, invariably they will throw a question on there that has to do with the cis and trans. Okay? Why? Because what they're pushing to and looking at is, do you understand the mechanism? Do you understand where those bonds are making and breaking? And if you don't, you'll see answer choices with them being cis or trans and potentially get the answer wrong because of it. Okay? The next thing, what happens? Okay. We now get the reaction step 2 with our H2O2 and NaOH. And what happens there? Okay. So we have a suggestion. Again, the wedges and dashes are ultimately irrelevant here, okay, but we're still going to show them because it does become important for this last little piece. Put that hydrogen on. Okay. What we just heard was that we do some goofy mechanism, okay, because it is a goofy mechanism. Okay, technically you didn't say goofy mechanism, you said backside attack. Okay, but your result is that you're saying after this goofy mechanism happens that you get this. Yeah. How does the boron react?
How does the boron react?
Mm-hmm.
It's substituted with OH.
I didn't ask what the end result was. I said, how does boron act?
It leaves. It's leaving group. Isn't that what it is if it's doing a backside attack?
If it's doing a backside attack, absolutely, I completely agree.
But it's not doing a backside
Okay? Why is it not doing a backside attack?
Technically, that carbon is negative because it's more electro.
There's an interesting point. If we're talking about hydroxide somehow coming in and doing a backside attack, what are we producing? We're producing BH2 minus. We're forming a negative boron. Can boron stabilize that negative charge particularly well? No, why not?
Very small.
Small and electronegative. This is a step above hydrogen and below at the same time because it's bigger than hydrogen, so it can stabilize the negative charge better, but it's less electronegative than hydrogen, which means it stabilizes the charge worse. Okay? So if we're talking about bottom of the barrel, if H minus was bad, guess what boron is? Sitting right there with it at the same bottom scrape in the barrel. Okay? So that's not how it reacts. Boron is not a good leaving group, so we can't run the mechanism as we're suggesting here. Which again, I will go back and ask, how does boron react? And again, everybody's like, well, I don't know. Okay, well, where are we? We're at 16 minutes into this lecture. What I would recommend you do is we rewind back the lecture about 5 minutes. How does boron react at the very beginning, our BH3? As an electrophile. Why? Because what's its hybridization? sp2. What's left over? An empty p orbital. Take a look at the product that we're now talking about. Tell me how that boron's chemistry has changed. It hasn't. Oh. So what does it want to do?
Go to something with electrons.
Where do we have something with electrons?
An OH perhaps.
Okay, and we could try and go out to the OH minus. Okay, and it turns out the OH minus isn't really there to do that because what the OH minus is going to do instead is act as a base. Where is there something remotely acidic?
Hydrogen on the carbon.
That's closer to the OH as drawn, assuming there's not an error in what I've got drawn versus what's being displayed. The H2O2. Why does that become important? Well, what happens? This pulls the hydrogen off, puts the electrons there, and what do we end up forming? O negative, OH. What happens? Boron's not happy with that, right? So it ejects electrons. Where does it eject electrons to? Fortunately, we're going to get an awesome Ghostbusters moment here. What did we just do? Oh, really? Oh my God.
Yeah, crossing the...
We crossed the streams.
Yeah.
Ah, Ghostbusters. Kids these days. Okay. Does that mechanism kind of look familiar?
It's the one we did earlier.
It's literally the exact same mechanism that we just did. Nothing's changed about it. Okay. What does that mean about where our OH should be? Should it be wedged or dashed?
Should be... Let me think about that.
It's a hard one.
Well, it shouldn't be dashed because it's not what we filled. It has electrons there, the boron.
So there's our carbon, there's our boron, there's our negative oxygen, there's our OH. If this is wedged, what happens? These electrons come up, hit the boron. These electrons come out, hit the oxygen. Those shuttle the electrons back over. could these electrons, our green electrons, go whoop to the back side of the carbon so that it could then form the bond with the oxygen? Okay, so we get one option that doesn't have time to. Time's a relative thing. Those electrons are officially moving through a hybrid orbital that could pop back and forth through the atom. So I don't quite accept that. Where's the oxygen? Is the oxygen behind the carbon? No, it's sitting right on top of it. Which means it's in the exact same configuration. It does not change. Okay? So we're going to pull this off with pens. I doubt I can pull it off with pens, but let's see what we can come up with. Right? There's our boron out there, the pen, kind of coming at you, right? Okay. Here's our OH minus coming down. It's doing this. Right? Okay, our bonds break.
Makes sense.
Still coming at you. Okay, officially it'd be a little bit more like that. Okay? But ultimately all that's happened is a slight rotation there. You're not coming in from the backside. You're not umbrelling the structure, the rest of the bonds away. It's coming in from the exact same orientation. You get the exact same configuration. This configuration is technically known as a retention of stereochemistry. How often does that happen?
Not super often.
Yeah, not super often, which means how often is it tested?
All the time.
All the flipping time. So yeah, you got to watch out for that. Okay. Again, do we care?
No,
Why not?
it's not chiral.
It's not chiral, so it's not a big deal. We don't have to stress necessarily about it, but it is something we need to be aware of as far as the region of that chemistry and how it functions and runs. Kind of, sort of? Okay. Is it also vastly more complicated than what I've just drawn?
Probably.
Yes, it's stupidly more complicated. Don't stress about it. This is let's just focus on where the little things are and not about the big structure. That boron forms insanely large, massive macrostructures. It's a mess. If you want to look at it, you can look at it later. Okay, so now what happens?
Probably would react with the PCC.
Now we can move to PCC. What is PCC? It's an oxidizing agent. And if it's an oxidizing agent, what do we expect to happen to our product?
To lose
Okay, be oxidized. So you're going to go, a loss of electrons. Okay, what's the oxidation state of any carbon drawn on the board? Okay, your definition of loss of electrons is a pretty trash definition if you can't tell me the oxidation state of any of those atoms. Yeah. And if you try to use your Gen Chem rules, you're also going to hit issues. Because in our Gen Chem rules, when we assign oxidation states, we make a really big assumption with that whole process that you learned back in Gen Chem. The assumption we make is that every element of that type has the exact same oxidation state in that compound. Okay? Which is true when? For all of the things you did in Gen Chem. It is not true for any of the things we do in OChem. Okay? Which means determining the oxidation state based off of loss and gain of electrons is generally not a good approach. Why do we call it oxidation? And for those people who go, well, it's loss of electrons. Loss of electrons does not sound like oxidation state to me. So I'm going to say no.
Well, it's probably because an oxygen is attached to it.
Oxidation is in direct reference to a reaction with oxygen. So when we oxidize something, we increase the amount of oxygen bonds. So if PCC is an oxidizing agent, it's causing something else to be oxidized. Which means our organic structure that we're looking at, when it reacts with PCC, should have what happen to it?
Gain an oxygen.
It needs to gain an oxygen. Okay? There are some caveats within that. This reaction look familiar? more or less?
Yep.
What chemical reaction is this? Awesome. Substitution is this oxidation reaction.
Oxygen's being added. So maybe.
Turns out it's not, but an oxygen is added. When we talk about our oxidation reactions, it's not just that we increase oxygen. Another thing must also happen simultaneously. Also have to lose hydrogens. Okay? Oxidation and reduction happen hand in hand. Okay? So when we talk about running an oxidation reaction, we have to increase the bonds to oxygen and decrease the bonds to hydrogen at the same time. And if we go through and look at the chemical reaction that's shown below, you might say, well, didn't I decrease the bonds to hydrogen? I have a hydrogen floating off. Our focus is on the carbon. What happened? That carbon lost a bromine, gained an oxygen. Did we change any bonds to hydrogen at that carbon? Nope. Which means its oxidation state does not change. Could you calculate oxidation states? Yeah, go back to like one of the first early chapters in our textbook, and Cardy talks about it, and ultimately we don't care about oxidation states for the most part, and we focus on formal charges. Formal charges help us predict where chemistry is happening without having to deal with oxidation states. Okay? So if we go back now to our structure, okay, and I want to increase the bonds to oxygen, what could I go through and do?
Maybe remove the hydrogen,
What hydrogen?
the one attached to the carbon.
Okay. So now, because that's an interesting point, do we remove hydrogens connected to oxygen or carbon? Where's our focus? Well, what's the class?
Organic chemistry.
Organic chemistry, and organic chemistry centers very carefully on carbon. So when we're talking about oxidation, we are very particularly talking about the removal of hydrogens connected to the carbon, not to any other atom. Okay? So we could go through and we could do this. Why would that be an oxidation?
Because it loses a hydrogen, gains an oxygen.
What hydrogen did it lose?
The one on the carbon.
Be very, very specific about your hydrogen. Would you say?
I was just gonna say the hydrogen on the carbon.
Be more specific about that hydrogen. What charge did the oxygen come in as? A negative, which means the hydrogen had to come off as
A negative.
also had to come off as a negative. Okay? That's why it's very specifically an oxidation reaction. You're getting the electrons to flow opposite directions you would expect. Okay? That is challenging and nuancing to deal with, and that usually requires a special reagent to allow for the electrons to shift around so that you can get these decent structures. Which takes us back to PCC. Not quite yet. When we think back to Gen Chem and oxidation and reduction, what did we very particularly tend to focus on? I said very particularly tend to. A bit of an oxymoron. What's your classic oxidation reaction?
Rust with iron.
Rust with
Iron.
iron. What is iron?
Metals.
Metals. So when we're talking about oxidation and reduction, almost exclusively we focus on metals because we're talking about how metals can transfer electrons around. Why? Because that's the characteristic of metals. Inorganic materials aren't metals, so they can't do oxidation reduction, right? Wrong. They can when facilitated by
Metals.
metals. Guess what that C stands for?
I was going to say, there's a lot of metals that start with C, dude. There's copper, chromium.
Yeah, I know.
A couple others.
But it's chromium. Okay? Technically, it's not chromium, it's chromate. Okay? So, but chromium is the center of what's causing that oxidation reaction to happen. Okay? Chromium is a very good oxidizing agent, and that becomes problematic. If it is very good as an oxidizing agent, what is it going to do?
Oxidize.
It's going to oxidize. It's going to oxidize what? Everything it can. All right, well, what's everything it can? Well, wherever there's a hydrogen bonded to carbon could potentially be a site for oxidation. Okay? But if that's the case, what do we end up with?
Multiple products.
That was to not breathe in Josie's face. but I'll do it again.
Oh, wake me up.
Is that a sigh?
It's not a sigh.
Oh, combustion.
Okay? If we talk about oxidation reactions, decomposition is our classic oxidation reaction. It takes any of our organic molecules with carbons and hydrogens and turns them fully across to carbon dioxide. We took all of the hydrogens, we removed all of the hydrogens, and we maxed out all of the bonds possible on our carbon with oxygens. That's a full oxidation. The problem with that, what do we know about carbon dioxide? Yeah? That's it.
We breathe it out.
We breathe it out. Is that it?
It's a carbon with oxygens connected to it.
It is true. It is a carbon. You don't know anything else about carbon dioxide. Depending on who you talk to, you can go inorganic or organic. I think I would typically classify it as inorganic. God, it's hot today, right? Why is it getting so hot? Global warming.
Oh, greenhouse.
What's one of the things that contributes to global warming?
Carbon dioxide.
Carbon dioxide. Why is carbon dioxide a problem?
Greenhouse gas.
Right? Yeah, it's a greenhouse gas, but there's other things that are greenhouse gases that we prevented. Okay, what is it? The polyfluorocarbonate? I don't think they're carbonate. Polyfluoro.
You're talking about
P-
PFAS?
No.
The
one that was in aerosol cans way before your time that they removed because it was a massive greenhouse gas issue. It-
For our
it's
time
a-
being the big statement there.
I know technically there isn't that much, before your time at this point, but we're talking about 80s and 70s. Okay, it was a really big issue, okay, within the 80s and 70s and pushed up into the 90s, and what they got rid of was, when you think about aerosols, there was a particular compound in it. I want to call it PFCs, but I can't think of the name, but it's PCFs? I don't know. It was a little gas, and that gas provided pressure, and it released off. And it was naturally non-toxic, so we said, oh, it's not a big deal, except it rose up into the air, and it acted as a greenhouse gas. Scientists were like, this is a massive issue, stop making those things, and you know what happened then?
Stop making those things.
Amazingly, people listened to scientists, and we stopped making those things. We since changed things around a little bit, and that's not necessarily working out great for us, okay? But that's what happened, and we no longer have that as a potential problem. We talk about the expansion of what's the thing at the ozone depletion, the hole, okay? That hole almost went away. Why? A large part of it had to do with these polyfluorochlorocarbon structures. You looking up? Polyfluoro? Poly. Where's the poly? CFCs. Okay, chlorofluorocarbons. There it is. Or CFCs. Okay, and we got rid of them. The ozone started to come back, and we were like, oh, great, everything's all swell and fine and dandy, and then we just burned all the petroleum up, turned it into carbon dioxide, and replaced the CFCs with carbon dioxide. What was the issue with CFCs? We couldn't get rid of them very easily. They don't biologically decompose. What about CO2?
Is it inert?
The same issue. CO2 is an insanely stable molecule. It is not easy to break apart. Okay? So if we talk about organic chemists, going back to this, okay, do we want to take it to CO2? No, because once it's CO2, we're screwed and we can't do anything with it. So when we talk about our oxidation, we do want to oxidize, but we want to oxidize in very particular locations. If we take a look at our carbon structure, we've got 3 carbons. Which of those 3 carbons do we think is most likely to oxidize? 1, 2, or 3? 3? Why? It's already next to a polar atom. That polar atom changes the chemistry enough that that carbon now becomes a primary target for our chromium structure. And we can oxidize it. When we talked about oxidation, what did we say were the rules?
You have to lose a hydrogen and gain an oxygen bond?
We had to lose a hydrogen and gain an oxygen bond. What's special about that carbon 3? How many hydrogens are there? There's 2 hydrogens, which means what could potentially happen?
You would lose 2 hydrogens and gain 2 oxygen bonds.
Ah, we could go through and run the system where we lose 1 hydrogen and gain an oxygen bond. Or we could run the system where we lose all 3 and gain 3 oxygen bonds.
But isn't that more stable than CO2?
That's a lot. Right? No, it's significantly less stable than CO2.
I don't get this shit anymore.
Or sorry, yeah, no, less stable than CO2. Okay, why?
I don't fucking know.
It's supposed to make a ketone network.
What structure have we drawn here for the first one? We'll call this one structure A versus structure B. What do we have for structure A?
Carboxylic acid? No? What is it?
That's a functional group that we talked about in this unit. It's a hydrate. And what do hydrates do?
They hydrate.
They revert to the carbonyl.
Oh, shit.
In this case, it wouldn't be a ketone, it would be an aldehyde because there's still a hydrogen connected there. Okay? The other case is an uber hydrate. Are uber hydrates any more stable? No. So let's go ahead and fix that. Let's take those 2 that are part of the hydrate and turn them into a carbonyl. Bingo! An aldehyde or a carboxylic acid. Why are these still more reactive than our carbon dioxide? We still have that carbon-carbon bond. That carbon-carbon bond is a handle that we can react with. As soon as I drop an oxygen onto that, now my molecule is pretty much shafted. Okay? And I'm stuck as CO2 or the varying forms of bicarbonate. Right? Why is this a problem for us? Well, if we're talking about oxidation in its limited sense, we're only targeting that primary reactivity at that carbon number 3. Great. But we have 2 possible oxidations we can run. We can go whole hog all the way to the carboxylic acid, or we pause and we stop at kind of a partial oxidation. Well, how do we decide which one to do it?
Compare the stability.
Based on the strength of the oxidizing agent.
This has to do with the strength of the oxidizing agent. Is it a strong oxidizing agent, or is it just meh? How would you know?
Did you say chromium was a very good oxidizing agent?
I did.
So would it go to the carboxylic acid?
So we'd say to the carboxylic acid, what's the other oxidizing agent you guys are going to be responsible for?
CO4.
Isn't it just chromium?
The PCC is supposed to just
We'll get back to that. The other oxidizing agent involves what metal? Chromium. So we have 2 oxidizing agents that we need to know. Both of them involve chromium. So our statement of, well, because it has chromium, so it's a strong oxidizing agent, becomes a problem because we have 2 oxidizing agents and both of them involve chromium.
Are both of them strong? Oxidizing
No.
agents?
One of them is weaker than the other.
It's because of the oxygen's on it that makes it weaker. Or
Which is a fun one too. Let's push on that. So this first reagent up here at the top, I don't know what we'll call that one. Okay. This is typically referred to as chromic acid. The active oxidizing agent is the chromium or the chromate. Okay. If we look at our PCC structure, guess what the active oxidizing agent is?
The chromium.
CrO4 minus 2. The fuck?
So it's just the presence of an acid versus the not presence of an acid?
But if we said the C was for chromium, what was the other part? What was the PC?
Poly?
What is PC humor?
Personal computer?
Really? You can't figure out PC humor.
Politically correct?
Politically correct. And as we all know, politically correct humor just sucks. Okay, we don't want that politically correct stuff because it's not quite as funny. It's not quite as strong of a belly laugh that comes out of it. Which means when I work with PCC, It's politically correct chromium, and it doesn't oxidize all the way. It stops. It only does a single oxidation.
Well, why would that change?
Okay? For the record, PCC does not stand for politically correct chromic acid, in case you didn't already guess that. What the PCC stands for is this. What do you think the C stands for? The chloride? What's the P stand for?
Phenol?
It's not a phenyl, it's got a nitrogen in it.
Oh, shit.
But good guess, you're thinking of P words, because it is a P word.
It-
Pyridinium. And you're like, I didn't know that. Don't worry about it. You didn't need to know that. Right, you should have known that because you watched the video on it where we talked about it's pyridinium chlorochromate. So when we go through and look at this, we get pyridinium chlorochromate, or PCC, versus chromic acid. Straight chromic acid oxidizes like crazy. Pyridinium chlorochromate does not oxidize. Well, ultimately, what's the difference between those two? Okay. First, before we even get into that, because I think it's a fun question to get at, and I'm going to blame Anthony. Anthony asked, he was like, well, why? I think you said it less goofy than I just did, but you did ask why. So we'll work on that. PCC, technically, this is the proper structure, but really what we do is we take the chromate, just like we did with the other one, we take technically potassium dichromate, we add it to a solvent. That solvent happens to be pyridine. Guess what pyridine looks like? Looks like that.
Just doesn't have reach.
Just doesn't have the H. Okay? Well, how do I get the H in that Cl?
Hydrochloric acid.
I add hydrochloric acid. Okay? Hydrochloric acid is a strong acid. Guess what the nitrogen is on our pyridine? Basic. It picks up the hydrogen. Okay? And we end up with pyridinium chlorochromate. So that's the reagents that come together to make PCC. What are the reagents that come together to make chromic acid? Okay? Well, again, we take the chromate and then we take sulfuric acid. Okay? Well, what am I dissolving it in? H2SO4. What phase is H2SO4?
Is it aqueous?
It's aqueous. I take H2SO4 and water and I mix it with the chromate. What does H2SO4 act as?
Acid.
An acid. What does HCl act as?
Acid. Strong acid.
So is that a difference?
I mean, is sulfuric strong? I can't remember.
Yes, sulfuric acid is a strong acid, so is HCl. They are both strong acids.
Water's not a strong acid.
Cool. What's the difference between water and pyridine? The ring does have an effect. What's the chemistry that we see when we look at water versus pyridine?
Oxygen versus nitrogen. That's where all the chemistry lies.
True. What is said chemistry?
Acid base.
Could act as acid base. What else could it do?
Nucleophile, electrophile.
Nucleophile, electrophile. Can the nitrogen act as a nucleophile?
Yep.
Can this nitrogen act as a nucleophile?
No, it's too big.
It's too bulky. Because it's too bulky, it can't act as a nucleophile. That's what shuts down the chemistry for pyridinium chlorochromate, is the pyridine can't react as a nucleophile. So when we run our first oxidation step, what do we end at? We end with the aldehyde. That's a polar pi bond. And what can the polar pi bond do?
Resonate.
Okay, I accept. We can resonate, and what does that show us?
Partial charges.
An electrophilic site. And because water can act as a nucleophile, water can come in and attack, forming what?
OH.
The hydrate. The hydrate, the alcohol form, is what reacts with the chromium. That's why alcohols get oxidized with the chromium reagent. They're reacting with the alcohol functional group. Pyridinium chlorochromate does not ever form the hydrate. Because it never forms the hydrate, can it oxidize a second time? Nope, which is why it stalls at the aldehyde. That's pretty fascinating. What's extra fascinating? We could test this. We could take pyridinium chlorochromate, that pyridine solution, and be like, well, if water's the issue, if water's what's causing the second oxidation, what do I have to add to that pyridinium chlorochromate solution? It's real simple. Add a little water to it, see if it oxidizes all the way. Guess what happens? It oxidizes all the way. The only difference between those reagents is the presence of water. What's extra fun about that? Take a look at our chromic acid. Do you see water written up there? No, because it's implied within the system. That's the only way you get sulfuric acid into this. Yippee!
Then why even add the sulfuric acid? Why don't you just add straight up water?
So deciding on how the mechanism works, why do we add the acid or, in other scenarios, add a base? Well, what's the point of adding acids and bases?
To protonate or deprotonate?
Why would I protonate and deprotonate?
To get a more stable product?
If I protonated the aldehyde first, what would happen? Yeah, I have this resonance structure, right? Which of these two scenarios is more likely to react? What's that? Top or bottom?
Oh, top or bottom? Probably bottom,
Why?
because O doesn't like being positive.
Okay. Ultimately, we look at the top one, what happens? We produce both a positive and a negative charge. That's destabilizing. We look at the bottom one, do we get two charges? Nope, we only get one. That lowers the activation barrier for that particular reaction. The acid changes the mechanism to lower the activation barrier. So why do we add the acid? We have to add the acid so that we can protonate, so that we can actually get the reaction to happen at a reasonable rate. Right? So it's changing our mechanism. That's looking at the hardcore detail behind it. The clutch step that differentiates why we will oxidize more for the other has to do with the presence of water, and that has to ultimately do with that hydrate state.
So we keep the sulfuric acid at the end of the reaction, correct?
Yep, sulfuric acid is reformed at the end, just like the HCl is reformed at the end as well.
Gotcha.
Right? Which goes back to our previous video on acetals, and we look at acetals and the formation of hydrates versus hemiacetals and all those fun things. Acid catalyzed worked better than not catalyzed. Because it, again, changes the intermediates along the way, changes the energetics, and allows that reaction to happen faster. Hooray, energetics. Right? Which is all fine and dandy, but Ivan's probably sitting there being like, God, just wanted to know structure B. Right? But since everybody wasn't on the same page, we had to go through and address all of those indistinct or distinct little pieces along the way, and we now have a broader sense of what's happening within this overall reaction and to those particular reagents. Right? Bottom line, we can delete all of this, and that can take us now back to what the hell was structure A?
I already forgot.
It was an aldehyde.
Oh, yeah.
So now we can go through and take a look at the structure B reaction, and we add Mg and THF. What kind of Mg are we adding?
Solid.
Solid. What does that sound like a red flag for?
Grignard.
That sounds like the formation of the Grignard. We could go through and draw all the mechanism stuff. Ultimately, it's not that big of a deal, so I wouldn't stress about it as long as you acknowledge that you can then go through and form the Grignard. What's special about our Grignard?
It's as a base.
We've got that red bond. That red bond is an ionic bond, which means we can effectively ignore the magnesium and we can acknowledge that we have a negative charge, on that carbon, and that negatively charged carbon could very well act as a base or a nucleophile. So we get both of those potential options coming out of this. Okay. To decide what we need to move on with, we would then bring in structure A. Structure A comes in and shows us this. What's the chemistry of structure A?
You want to depronate the alpha carbon, the carbon alpha to the carbonyl.
Okay. Now trying to decide where should we run the reaction. Okay. So I do like your added language of saying the alpha hydrogen, so you're talking about this one. Okay. We definitely don't want to touch the aldehyde hydrogen. That is not acidic. So we could try and manipulate that alpha hydrogen. And this one I don't have a good answer for, unfortunately. Okay. What I'm going to push it to is that we're likely looking at an actual steric issue. That the Grignard reagent is so sterically large that that hydrogen is not easily accessible. What is easily accessible?
The pipe.
The electrophilic carbon, where we're looking at the p orbitals, above and below,
This
away
is fucking
from those.
bullshit, Mike.
I completely agree.
With the other Grignard, I said steric hindrance every goddamn time. You're like, sorry, no steric hindrance here, bud. Okay.
Which is right. There's no steric hindrance in the reaction with the carbonyl. There is steric hindrance in the reaction with the alpha hydrogen. So I'm still consistent in my logic. Yes!
God, this fucking sucks.
Yes! You're welcome. Ah.
You get some sick pleasure from this.
I've actually wondered about the alpha hydrogen being acidic versus not. And I haven't spent the time to actually figure out that reason. So I have that exact same question. But yeah, the only explanation I've got right now is that you're picking up some kind of steric issue with that hydrogen versus the carbonyl being slightly less sterically hindered because you're reacting a different plane.
But yeah, but we wouldn't. You still probably get some of it in our product. No?
Yeah, so that now pushes to potential byproducts or side products and things like that. Right. So we now have this potential structure. So now what happens? We now follow it up, as we do with all Grignard reactions, a second step, if you will. Okay. We protonate, and we end with our alcohol species with the phenyl connected. And we're now all the way through the gambit.
Couldn't you theoretically increase your yield with this by making the Grignard even bigger by increasing that steric hindrance? Or would that at that point start messing with its
So that could be how you would study whether or not it's going to do the carbonyl chemistry versus the acidic hydrogen, like maybe vary the size and see if you pick up some of that alpha hydrogen. You're not going to see the alpha hydrogen as a product because that's not a product. What you would potentially see is if you deprotonated the alpha hydrogen, do you get the aldol product coming out of that? Okay? That aldol product is a whole nother can of worms and potentials within those systems. Okay? And so could you play around with that? Sure. Have fun. Let me know how it works.
I suspect there's some intricacies.
There are probably some intricacies behind it, and it's, yeah, that base characteristic is one that gets me because I would think the alpha hydrogen is acidic. If we have an OH, we deprotonate the oxygen. That hydrogen on the alpha position is at least as acidic as the OH. Why is that one not deprotonated? And the only thing I can come up with is that you're looking at that one being sterically hindered relative or in comparison to the carbonyl, because the carbonyl is the pi system that you're reacting. That's all I've got. And I am, full disclosure, completely pulling that out of wherever you want to describe me pulling that out of. Okay? Are we good with that?
I'm taking a picture. Close it.
Okay.
You son of a bitch. I remember this one. You might win this battle, but you'll lose the war.
Okay, are we good?
See you.
Yeah, just sitting there waiting.
Just the face, like, waiting.
Are we good? Can I clear it actually officially?
Yes.
Okay. You said question 1. This is going to work. You haven't even attempted this one. Why should I help you with this one?
Because I'm not sure what it's even asking.
Retro symbolic analysis for the compound unit.
Right. So to the what it's even asking, it's asking you to think backwards. Okay. So these arrows, and I, full disclosure, don't particularly like this. It always kind of bothered me, and I don't understand why we can't just flip the whole thing around and go the other direction. Okay. But those arrows are very specifically saying product on the left, reactant on the right. So what we're saying for compound A is if I had compound A, I would react it with something to make the thing on the left. Okay? Is that confusing? Yeah, I don't get it. I really don't. I just don't understand it. Okay? So for me personally, what I would try and do is not forget what the structure was. As we would reformat this a little bit. Right? And so what I would do as kind of a rethink, what was those words? Precursor to compound C. Yeah. As I would say, I am starting with this molecule. I make compound C. I then bring in compound B. Okay, and I'll address that arrow here in a second. Okay, to produce compound A, and then compound A reacts with something to make this final thing. Okay, that's what I would change to it. What's the deal with me showing the compound B coming in this way? Okay, what I'm trying to accent there is that this alcohol, cyclopentanol, okay, reacts to make compound C. It doesn't make compound B. Compound B is an unknown that I bring in to react with compound C to then make compound A. Compound A then reacts with some unknown structure to make my final product. Okay? Some questions that I would ask. Okay? To run this, I need some reagents in this block. Okay, we'll call it block 1. Okay, I need reagents here in block, we'll call that block 3. Why are they saying compound 2 is block 2? And they're actually putting in B. Why don't they just say it reacts with something to continue across? Why is the notation different for my second step of the reaction from my first and my third? You're making a funny face at me, which I think means you don't understand my question, which is okay.
Because it's our intermediate?
It's not, because C is an intermediate, A is an intermediate along the reaction.
Yeah, but I guess it's not intermediate itself.
Right, to try and help clarify you, why aren't they just saying we do this? I take the alcohol, I react it with something to make C, I react it with something to make A, I react it with something to make 3. Why are they telling me that step 2 has some B thing in it? Why is that useful information to me? Does that help clarify it?
Maybe compound A has 2 products that react with each other?
I don't think so. And I honestly, I don't know the answer off the top of my head. I've got some guesses.
Because of structure, not
Trying to think through what the answer is. Oh, I just got it. God, I love when that happens. Compound B, I would argue, is exactly what you're saying. Compound B is a structure. Well, aren't all of these things structures? So elaborate. I agree with you. I think you're on the right path.
guess like a ring, but just.
Can't be a ring, because if compound B was a ring, how many rings would I see as a product? 2, so I don't accept that.
Are you saying it's a product of A?
Nope. Almost everything's going to have a charge. But is it something that has? Yes. There's a B is something that has. Nope. Carbon.
Oh, okay.
That's all it is. If we look at structures, reactions 1 and 3, 1 and 3 are being used to just change functional groups around. We're not changing the structure. Reaction 2 is changing the structure by adding carbons into our structure. Okay? So B is the carbon source that comes into this.
Is it also the nitrogen source?
Well, that's an interesting question.
Consider
Is it also the nitrogen source? Okay. So how would we decide that? Okay. So potentially said another way, I'm just going to float the B up there like that. Everybody okay with that? Okay. Knowing that structure B is bringing in the carbon can be, or a carbon, at least a carbon, is helpful. Okay. What else could it potentially bring in? Why are you saying now, asking, is it also supplying the nitrogen? What makes you think it's supplying the nitrogen?
Because basing off the reactant in the final product is that there is, the addition is a methyl that's connected to a
Okay.
H2.
Is everybody tracking that? So we compared reactant to product, and the biggest difference that he sees, number one, is that we have that extra carbon. So with this hint that structure B is supplying carbon, okay, that carbon is likely coming in with structure B. But if we take a look, the nitrogen isn't in our starting structure, which likely means structure B is bringing in this entire piece. Okay, how it brings it in is a whole nother can of worms, and we'll address that. Okay, but that should somehow be coming in from structure B. So what does that tell us about structure C?
That it must just be moving around a functional group, I suppose, if that makes sense.
I asked that question, and it was, I think, a dumb question. So here's some context about what structure B is. Okay? Structure B, if we think about it, right? What charge? Yeah. Which part of structure B do we care about? The carbon or the nitrogen? Which one do we think is reacting?
The carbon,
Why?
because it's connected to the main structure.
Awesome. The carbon's the one that's directly relevant. Okay? What charge do we think that carbon was?
Negative.
Why do you think it was negative?
Because the alcohol would cause there to be a partial positive charge that the carbon is attached to.
Awesome. If that's coming in as negative, okay, the guess is that that carbon is likely to be positive. Was it? Yeah, it's an electronegative oxygen connected to it. Okay, so that has a large partial positive, which means the carbon that's coming in structure B likely has to somehow be negative. Okay, whether that's a lone pair or not, that's why I erased the lone pair. We don't really know, okay, yet, but we have some context here. Okay. Could I just take a negative carbon and directly attach it to that positive carbon? Would that work?
Probably not.
Why not?
A negative carbon is not very likely to be stable. It would be so unstable it would react with whatever.
I've got Grignards. So I can make negative carbons.
Yeah, but that's stabilized with resonance.
It's not resonance stabilization. It's within the magnesium in the solvent is stabilizing it.
So
So
yeah.
that could be other things that are contributing to stabilize that. I could say, well, I'm going to also include magnesium, the bromine, and THF, or diethyl ether. Okay. So all of those things don't prevent me from having a negative carbon. Okay. So I can create a system that would allow that negative carbon to come into existence. Would I expect that negative carbon to form a bond to that Why not?
Because that negative carbon reacts with C, not with that first structure.
I don't even care about that. I get what you're saying, but I don't care about that yet. Why can't I just say, screw C, negative carbon, poof, directly attack?
Wouldn't it be more likely acting as a base?
Okay, there's an option. If I had a negative carbon, where would it likely react? It would react with the hydrogen connected to the oxygen, which it clearly does not do because that hydrogen is in our final answer. And I need it to connect to that positive carbon. Okay? So could it directly connect? No, it cannot, which means we have to do something here. In that have to do something, we just address one of the things we have to fix. What's one of the things we have to fix?
Where it will react,
Because what did we say it would react with?
the hydrogen,
The hydrogen. So minimally, C has to
not have that hydrogen.
not have that hydrogen. Okay.
We love a carbonyl.
Why do you want to form a carbonyl? Because that's a bit drastic. I just said let's get rid of the hydrogen, and you're like, carbonyl.
Because it would make sense.
Yeah, but
Do better than that. Jiminy Christmas. Just makes sense, Mike.
What about the octet?
So there's an interesting dilemma. What do you mean octet?
Well, there's an implied hydrogen.
There is an implied hydrogen on that carbon. Okay? So if we ignored the hydrogen and just said, okay, let's not make it a carbonyl, and just said that that was a negative carbon, would this negative oxygen, would that negative carbon be willing to come in and attack that spot? No, why not? Couple reasons.
Steric hindrance.
Steric hindrance, keep going.
There's that implied hydrogen.
There's that implied hydrogen, which means we need a leaving group and all of that. Okay? So what could we do instead? I don't want to have this weird octet issue, so what should I do to that hydrogen?
Get rid of it.
Get rid of it. But if I get rid of it, I'm now missing an octet, so what should I do?
Turn it to the carbonyl.
Turn it to a carbonyl. What happens to that alcohol hydrogen? Gone. I don't care about it. I don't need to worry about this. Now my negative carbon Grignard could come in and not react with that hydrogen. Okay? But if it comes in, do I have an octet issue? No, why not?
Resonance.
I break the pi bond. Lovely. That was easy. So the question itself, and actually I lied. The question is just asking compound A, B, C. Okay, and it didn't ask for the reagents, but that's the next level. How do I go from an alcohol to a carbonyl?
I mean, I suppose.
What?
Would acetal work?
No. Acetal's going the opposite direction at best.
Make rid of PCC.
You mean the thing that we just talked about doing with our oxidizing agents, PCC or chromium? Yes, yeah. Yeah, exactly, one of those.
Damn. Yeah.
Okay? Okay. Are we concerned whether we use PCC or chromic acid?
Yes.
No,
Why no?
because there's only one hydrogen.
There's only one hydrogen to remove. It doesn't matter which reagent I use. I can fire whichever one I want at it. Officially, which one should I choose? PCC. Why?
Cheaper.
Less toxic.
Well,
Okay. Chromic acid is going to oxidize everything like crazy. Let's use the one that doesn't oxidize everything like crazy. We want to use the reagent that allows me to do exactly what I need it to do with the lowest amount of activity as possible. Okay? So PCC could make more sense. Officially, we don't like PCC or chromic acid because,
they're both sort of toxic.
yeah, they're both stupid toxic, yeah. Okay, if you've heard of Aaron Brockovich, the whole point of that issue was chromium being leaked into the water.
I have no clue what you're talking
Yeah.
about.
Look up Aaron Brockovich. Again, it's now an old thing that happened, I think, in the 60s to 70s, not positive exactly,
Is it kinda like
but it
Flint?
was turned into a movie with starring Julia Roberts in the 80s, maybe?
Is it another water kind of like the Flint thing?
Similar kind of thing. Well, I don't know that Flint was intentional. In this case,
Oh.
I believe this was, and I'm not positive, so please do not quote me, and please do not sue me if you're freaking DuPont. I think it was DuPont was just like, we've got these waste products that we don't want to worry about. We're just going to throw them out the door. And all of those chemicals leached into the water supply, and then people in that town ended up drinking nasty water and killed lots of people, cancer, all sorts of fun, nasty stuff. And nobody paid attention to it because it was a massive chemical company and they could just out-lawyer anybody. That's where Aaron Brockovich, as a lawyer, came in and was like, no, we're calling you on this, and was able to win. Okay? Different story, different time, look it up. It's cool, it's interesting. Also insanely sad, and this is one of the reasons why people don't like chemists, because they're like, you guys are jerks, you kill everybody. You're not wrong. But there's a lot of chemists that don't kill people too. Like, let's just not throw all the baby out with the bathwater kind of a deal. In any case, back to our system. Okay, is structure B going to work? Can I just take this negative carbon and go whoop and have my final product? Why not? Couple answers for why not.
Because, well, you will form a oxygen with a negative charge. So it could be acid, having an acid after.
No. But I don't like that answer.
Could you just make A an acid and all this would work just fine?
I kind of have a cop-out, or a better cop-out answer than just no. Okay? What was our whole point of B? Why did they show B at all? What was it trying to do? Supply carbons.
Why couldn't the A have done that?
Which
That's what-
means if we're just going to react B with C, it doesn't make sense to show A as an acid because A should have carbons in it, just like B had carbons in it. Okay, that's my half-assed cop-out answer that's better than no. It's still not great, okay, but no.
But okay, so out of B and C, one of them is just being added, or both of them are. One of them is the product of.
So compound C and compound B react together to make structure A.
To make structure A.
A then reacts with reagent 3 to make our final product. Okay, so what I asked is, could I just take compound B with compound C and go to our final product?
No, you'd have to go to A first.
I have to go to, so that one cop-out is, well, no, it says you got to go to A, Mike, so you can't do that. Well, why?
Because it says so. That's the whole point of the question.
Negative carbon next to some potentially protic hydrogens. That's going to get a bit dodgy with our Grignard reagent. It could self-quench and kill the whole reaction. Okay. So I need a negative carbon, but I don't want protic hydrogens. Protic hydrogens are problematic, which means compound B has to somehow lose these hydrogens. But if I lose those hydrogens, I can't lose those electrons because nitrogen needs its octet. And if I did that, then I'd have this super negative nitrogen, and I don't like super negative nitrogens, so what could I do instead?
You could just throw in some pi bonds and make it not negative.
If I now drop those pi bonds into play, now what happens? The carbon will still be negative. Officially now, if we do Lewis structure, it is going to have a lone pair. The nitrogen won't be negative because its electrons are occupied into the pi system. That negative carbon can now act as a nucleophile and attack our carbonyl. The product of that was a pretty sad attempt at a drawing. Okay. Problem with showing that as A is that this is supposed to be a neutral structure. That can't be a neutral structure because the oxygen is now negatively charged. So what would we follow the nitrile up with? We'd probably follow it up with a little bit of H+. Okay? That would be probably the reagent 2 in a step 2 for that reaction. So we would have step 1 be the triple bond with the negative, step 2 adding H+, which gets us structure A, where structure A has the hydrogen connected to it. Now, how can I go from A to the final product?
H2.
What do you mean?
I mean, something that would add a hydrogen to both the carbon and the nitrogen at the same time. H2.
H2. Okay. Is H2 a particularly reactive molecule?
Yeah. I think, isn't it?
It's a gas.
I mean, it is a gas. That doesn't necessarily make it unreactive.
Wouldn't that make it more reactive, more movement?
It's very, very small. Because it's very, very small, it can't coordinate to that pi bond very well.
And put a shit ton of it.
It's still not going to coordinate very well. You want to maximize it. So you would need some kind of catalyst. Have we talked about, within the videos, any kind of catalyst that would help you add H2? Platinum. H2 and platinum. That H2 and platinum would absolutely add hydrogen to both sides of the pi bond, but we have 2 pi bonds, so it does it twice, and that would take us to our final answer.
So you're saying if we had a bunch of H2, it wouldn't? What else would it do?
It wouldn't react, it would just do nothing.
But if you touched it with platinum?
Yeah, to get the hydrogen reaction to do, what kind of reaction are we doing there?
And just acid?
It's not acid. If you go through and look, if we do
Oh,
resonance on
shit.
this structure, we have a positive
It's an
carbon and a
addition.
negative nitrogen. It is an addition, but we can get even better with it. What charge is the hydrogen being added?
Positive and negative?
And negative. Is a negative negative hydrogen particularly stable?
No.
No. What's the negative hydrogen being added through? A reduction mechanism. You're increasing the bonds to hydrogen while decreasing the bonds to an electronegative element, which we didn't talk about with our oxidation reaction because we didn't actually achieve that level. When we talk about oxidation,
It could be
oxidation
NO or F.
is anything more electronegative than carbon. Right? So that could be NOF, Cl, Br, I, all of those. It can also be carbon. How can carbon be more electronegative than carbon?
Induction?
I don't want to call you right idea. You're too high on the ladder.
Too high?
Yeah, you're never too high on the ladder, but you're too high on the ladder.
Oh God, isn't there something like where there's like a relative
Yeah.
electronegativity according to S or P?
Getting to the right idea. Hybridization effects.
Yeah, I know, but
So you can change the bonds or whether you have an alkene or an alkane, that's changing your oxidation state for the carbon. You're changing the amount of electronegative atoms connected because you have an sp2 versus an sp3 after the reaction, or flipping it the other direction.
So wait, which
Right?
one's
Those
more
do
electronegative?
count as redox reactions.
So is the sp3 or the sp2 more electronegative? It's the sp2.